The problem is this is a figure shows a horizontal force. So this force is horizontally being applied to the upper end of this lever. It is attached with the two springs, spring number 1 and spring number 2. Assume that the resulting motion is small, thus essentially horizontal, and determine the expression of the equivalent spring constant that relates the applied force to the resulting displacement. So now if you take the moments about O, since this is in a equilibrium condition, so all the moments they are, it's a very small displacement, so it's like a static equilibrium. So what you can do, moment of this force, remember moment is force times the moment arm. So for moment of this force is in clockwise direction. So if I draw the free body diagram, let me draw. This is my lever and this is my point O, and this is the force F, and this is my distance. This is so remember, let me explain to you. Remember the moment is defined as the moment arm times the force. The moment arm is the perpendicular distance between the line of action of the force, which is this, and the perpendicular this distance is L. So the moment caused this turning effect, or the moment, is the clockwise direction, because this will turn the lever into the clockwise direction. On the other hand, the force caused by this deflection, when you are compressing this spring, the spring force is equals to K times X. And you know the moment, how would you, this force times L gives you the moment of that spring. Let's assume this is spring number 1, although they have the same stiffnesses. So okay, we will just, to make it easy for you, this is K1, this is K1, and the moment of spring K2, Fk2 times L by 2, because this length from the perpendicular, the distance, the moment arm is L by 2. Agreed? And now what is Fk2? We know that the force of a spring is K times X. So in this case, so what is K times X? So I can write down here K times X as such. So K times X times L would be the this is the force, the deflection is X as given over here, and this would be, since it is linearly applied, so as the length increases, so it will be X by 2 over here, because this is half of the length, it will be X by 2. So I can write here Kx by 2 times L by 2, which this L by 2 is due to the moment taken about point O. So I'm going to write down now the moments, all the moments, combine all the net moment about position O, which is 0. So the right hand side, the negative FL, so the clockwise, and plus K mk1 plus mk2, this is equals to 0. Or I can write down now FL plus K times X times L plus K times X times L over 4. Or if you just equate it, because they are asking us to find out the equivalent spring. So equivalent, if you make this equation in this shape, then the slope, or the equivalent stiffness, would be the coefficient of X. So let's make this in that shape. So I can write down FL on the left hand side, and K L plus K by 4 L times X. 1 second. I can, yes, I can write down this. L is common, so can you see this is common, so I can just eliminate L from both sides. So I can write down, so this is my F 5 by 4 K times X. So this is my equivalent stiffness for this stiffness.